In this section, we will discuss the idea of random variables. To begin, let's start with a few definitions. First, we have that a random variable is the numerical outcome of a probability experiment. So we run some type of experiment, we collect the probabilities. One thing that we'd want to note in terms of notation, often when you see problems in the textbook, random variables are denoted with uppercase letters. So next we have a discrete random variable, so that additional word discrete to the random variables just tells us the possible values must be discrete numbers. And we've seen this earlier whenever we discussed the difference between discrete and continuous variables. Next we have continuous random variables, and they're random variables that can take on any value in the interval. And we know for a continuous variable, the possible values are not restricted to any type of list. So in our next example, we're asked to consider a coin tossed twice. So you toss the coin once, record the results, toss the coin a second time, record the result. Let x be the number of heads that appear. Here we see our capital X. This is representing our random variable, which is the number of heads that could appear in 2 consecutive coin tosses. And we're asked to find the probability distribution of x. And you can see I've got the table kind of outlined for us here below. Before you find a probability distribution, you first need to usually figure out what's the sample space. What are the possibilities that could happen? So if I'm tossing a coin the first time, I know I could get heads or tails. And then when I toss the coin a second time, I could again get heads or tails again. All possible outcomes from that are I could get heads first, followed by another heads. Or I could have had heads first, followed by tails. Or instead of having heads first, I could have had tails first, followed by heads. Or tails first, followed by tails. And if we list out this is our sample space of all possible outcome, we can start to list the sample space in related to x, the number of heads that appear. So for this first entry, this corresponds to an x of 2 because there's 2 heads appearing. For this next entry, this would be an x of 1 because there's exactly 1 head. For the remaining 2 entries, identify what value of x do they correspond to. So in our third entry, tails heads, we see we have 1 head, so that's x of 1. And in the last entry, tails tails, that's no heads. No heads would correspond to the number of 0. So I know the possible x values are 0, 1, and 2. So we're going to list that in our table, 0, 1, 2. And that corresponds to 0 heads, 1 head, 2 heads. Now whenever you find probability, remember from our previous lessons, probability in its simplest formula is just the number of ways what you're looking for could occur divided by the total possibilities. So we keep in mind this is our general formula for probability. So if I want to find the probability that I get 0 heads, there is only one outcome that gives me 0 heads out of the 4 possible outcomes. So that would give me a probability of 1/4, or written in decimal form, 0.25. Next, let's follow up and see what would happen if we were looking for the probability of 1 head. So where in our sample space do we see exactly 1 head? Well, that could be with our tails heads or heads tails. So there's 2 possible ways out of the total 4 options. So the probability in decimal form is 0.5 for 1. Similarly, can you think of how you would find the probability for x being equal to 2 heads? We look and we see the only option that would give you 2 heads is this 1. And that is 1 out of 4, or our decimal answer of 0.25. Now, as we create our probability distribution, that was what we were asked to do at the beginning, the final check that you need to do when it comes to a probability distribution is you should be able to add up all the different probabilities, and it has to equal 1. That's one of our rules for probability distribution. So let's check our answer here. So we've got our 0.25 plus 0.5 plus 0.25, and indeed they do all add to be 1. So everything checks out for this one. So let's just remember our key ideas for probability distribution. Let P of x represent the probability that a random variable attains value x. then each probability must lie between 0 and 1 inclusive. So I can't have negative probabilities, I can't have probabilities greater than 1, and if you add up all the probabilities in the table together, you have to get exactly 1. So those are 2 rules that we need to verify hold for a probability distribution. So in this problem, it asks us which of the following tables represent a probability distribution. The only 2 things that we have to check is first, are all the probabilities between 0 and 1 inclusive? And then if that works out, then ask if I add all the probabilities together, do I get exactly 1? So as you look at A, check the first criteria. Are all the probabilities listed between 0 and 1? As we scan through the probability column, we see the one that I've highlighted here, negative 0.3, that's not between 0 and 1. Since you've got a probability listed that's not between 0 and 1 inclusive, that means this is not a probability distribution for part A. So let's next look at B together, and then I'll ask you to check C on your own. So we know our 2 rules for probability distribution is all the probabilities must be between 0 and 1 inclusive. So we look 0.7, 0.25, 0.31, 0.22, 0.05. The reason I'm checking the entries in this column is they correspond to P of X, the probability. All of these are between 0 and 1, so that rule checks out. The next rule is if I add all these together, do I get 1? So let's check in our calculator. So here I'll add all these together, 0.17 plus 0.25 plus 0.31 plus 0.22 plus 0.05. And I added all of them together and I did get 1. Since both the rules check out, B is a probability distribution. Now for the next one, C, I'd ask you to pause the video right now and attempt this one on your own. When you're done, unpause the video and check your work. So here we check our first thing. Let's look, I find the probability, so that's all the entries below it. All of these entries are between 0 and 1, so that meets our first rule. My next rule is that they'll all add together to be equal to 1. So let me get my calculator and verify that. So we have 0.1 plus 0.17 plus 0.35 plus 0.38. They do add to be 1 exactly, so since both of the criteria are met, this is a probability distribution. So keep in mind if you're asked to verify whether something's a probability distribution, that goes back to verifying these 2 conditions are met. So next up we have the mean of a random variable, and you might want to keep this in mind. Our textbook currently is using mean of the random variable, but you might see in other circumstances the phrase expected value. They are the same thing. So if we have a random variable, we've got some kind of probability distribution, and it says the mean of a discrete random variable, the way that you can find it is you multiply each possible x value by its corresponding probability, then you add up all the products. So for instance, in the probability table that you see below, the process I would follow is I would take 0 times 0.2, its corresponding probability. Add that to 1 times 0.5. Add that to 2 times 0.2. Add that to 3 times 0.1. Now, in terms of mathematical notation, that entire process can be written here. I've got my mu sub x, so the mean of the random variable x is equal to the sum of all the x values multiplied by their corresponding probability. So you can work with the notation or you can remember the process. Both will work. So in our next example, it says a computer monitor is composed of a very large number of pixels. It is not uncommon for a few of those pixels to be defective. Let x, in this case, represent the number of defective pixels on a randomly chosen monitor. The probability distribution of x has already been given to us. So the probability that there's no defective pixels is 0.2. The probability that there's 2 defective pixels is also 0.2. The probability that there's 3 defective pixels is 0.1. And here we're asked to find the mean number of defective pixels. So we're asked to find the mean of this random variable and or the expected value, same thing. So what we'll do is we'll follow our process. So if this helps us visualize it, 0 times 0.2, 1 times 0.5, 2 times 0.2, 3 times 0.1, and then at the end we're going to add all of those products together. So let's write that out. So we have 0 times 0.2 plus 1 times 0.5 plus 2 times 0.2 plus 3 times 0.1. And now, depending on how comfortable you are using your calculator, you could either type this in all at once, or you could figure out each term separately and then add them together. I'll figure out each term separately and then add the total together. 0 times 0.2 is 0. 1 times 0.5 is 0.5. 2 times 0.2 is 0.4. 3 times 0.1 is 0.3. Okay, then we'll add all those together and we will get exactly 1.2 is the mean number of defective pixels. So if we were to make a statement for this particular set of computer monitors, we would say on average we expect there to be 1.2 defective pixels per monitor. So next up we have the variance and standard deviation for a discrete random variable. So here if we have a random variable, we've been given the probability distribution or we could find it ourselves, then we can calculate the variance and the standard deviation from these formulas. So to find the variance, we write that as our sigma. This is the symbol for sigma, sub our capital X, that's our random variable squared, is equal to this. So in notation-wise, we know this symbol represents the sum of all such terms. So that means add together all the terms that look like the x value squared times its corresponding probability. So you add all that together and then you subtract this mu sub x squared. Remember, mu sub x is the mean of the random variable or the expected value. So the variance does take a little bit of time to find. It's a bit more computationally not complicated, but we just need to be careful. But then once we have the variance, the standard deviation is very quick to find. We see that the standard deviation is just the square root of the variance. So basically it's saying spend the time, figure out the variance correctly, and then to find the standard deviation, you just have to take the square root of the variance. So as this reminder tells us below, if we find the variance, we can then easily find the standard deviation by taking the square root of the variance. And keep in mind, whenever you're working with square root in your calculator, y'all's calculators will probably have a symbol that looks like this. And if you don't see that on your calculator, but you have got exponent buttons, you could also raise the exponent button to the 1/2 power. Both of these are taking the square root. So let's read through this example. It says, in the previous example, we found the mean number of defective pixels for this probability distribution, and that's actually the example we just finished. And as I recall, we found the mean number to be 1.2. So that was our mu sub x, because it's the exact same probability distribution as our last example. And now we're asked to find the variance and the standard deviation. Now, based on what you see written above, think to yourself, should we find the variance first or the standard deviation first? We should find the variance first because we know once I've got the variance, I just take the square root and we've got the standard deviation. So let's focus on the first formula you see above. So the notation tells us that you sum, that's this capital sigma, the sum of all the things that look like x squared times the probability of x. So what I'm going to do is I'm going to square this x value, and then I can multiply the square of the x value by its probability. And you continue doing that. You take the next x value, 1, you square 1, and you multiply it by its probability of 0.5. Then you take the next one, you square the next x value of 2, multiply it by the probability it corresponds to 0.2. And you keep doing that and adding each of the terms. So I think here we will benefit from writing these out. And just a small aside here, as y'all do your homework or any type of studying for this class, make sure you have blank piece of paper, pen and calculator out, we can't be successful at math unless we actually work and do the math problems. So always make sure before you sit down for a video or before you sit down for your homework, have your pen, pencil, and calculator so that you can work through these problems by hand, type them into your calculator to finish it up. So here I'm going to work on this first portion. I'm going to say it's going to be the sum of all the x terms squared, so 0 squared, times its probability of 0.2, plus the next x term squared, 1 squared, times its probability of 0.5, plus the next x term squared, times its probability of 0.2, plus the next x term squared, times its probability of 0.1. And that gets me the sum of the x squareds times the probabilities. And then at the very end, once you've done that, you subtract 1 time mu sub x squared, so that's the expected value or the mean of the random variable. Now normally we'd have to separately calculate the mean of the random variable, but as this references our previous example where we already calculated the mean of the random variable to be 1.2, we could just substitute that here. But keep in mind in other problems you might have to separately calculate mu sub x following the procedure that we saw previously. So this should give me my variance. I've just got to make sure I type it into the calculator correctly. Now 0 times anything is 0, so the first term is 0, plus 1 squared is 1, times 0.5 is 0.5. Okay, 2 squared is 4, times 0.2, 4 times 0.2 is 0.8. You can also type this into the calculator. 3 squared is 9, times 0.1 is 0.9, minus, now 1.2 squared, 1.2 squared is 1.44, so I'm going to subtract 1 from 0.44 once I get the first term. Okay. Next, let's add these up. 0 plus 0.5 plus 0.8 plus 0.9, and that gets us 2.2. That's the sum of the x squareds times the probability, minus the mu sub x squared of 1.44, and we get a variance of 0.760. So here we were asked to round to 4 decimal places, so we'll type 0.7600, and that's what we'll label as our variance. And now we're almost done. We've got the variance. We do need the standard deviation, but once you have the variance, it's just the square root of the variance. So let's get our calculator out. Now everybody's calculator looks differently, but you can see on my calculator here is my square root button. So I'm going to do the square root of 0.7600. I get this value. We have been asked to round to 4 decimal places, so we look 8717. We look to the 4th decimal. Remember, then you look 1 past it. If it's 5 or greater, you round up. If it's less than 5, it stays the same. Past the 7 is another 7, which is greater than 5, so we round up. So this will be 0.8718 as my standard deviation, which is my sigma sub x. So let's keep in mind, what did we review in this video? We reviewed given a table of values and corresponding probabilities. How do we know if it's a probability distribution? You got to check 2 things. First, are all the probabilities between 0 and 1 inclusive? Second, do all the probabilities add up to 1? If the answer to both of those questions is yes, it is a probability distribution. If it even fails for one part, it's not a probability distribution. Next, we said for a random variable, if we're either given a probability distribution or if we find it first, we could then find the mean of the random variable, also known as the expected value, following the pattern that you take the x value times its corresponding probability plus the next x value times its corresponding probability, and you just continue that process throughout the table. And this is what we know notation-wise if we're ever asked to find this symbol, that mu sub x, that is the mean of the random variable, or the expected value. So keep in mind, in this class, we'll need to associate not only the verbal descriptions, but the notational descriptions as well. So start to associate mu sub x with the mean of the random variable or the expected value. Finally, we said for a random variable, we can find the variance and the standard deviation. The variance, the notation we used is sigma sub x squared. And it follows the process of adding up all the terms that look like x value squared, notice the square here, times its corresponding probability. Keep adding that throughout the table. And then once you finish that, you then subtract by the mu sub x squared. And remember, the mu sub x is what we just looked at, the mean of the random variable, also known as the expected value. Once you've got the variance, you can quickly find the standard deviation because the standard deviation is the square root of the variance. So I'd encourage you to get started on the practice problems. You know, the more you work with these formulas, the easier it will be. So have your notes out, work on the homework problems, and as you work with it, make sure you're clearly writing out your work. So you've got something that you can check, and the more and more times you practice, the easier it will get. So as always, if you have questions, don't hesitate to reach out to me via our campus communication, and I'll be happy to help you.